Hello and welcome to a digital lecture for Salt Lake Community College. This lecture will be a continuation of section 3.2 for Intro to Statistics, considering the normal distribution. Note that in this lecture, we will also be looking at the normal probability table available in Appendix A of your textbook. In the first lecture of 3.2, there were a couple examples comparing test scores from different classes, each of which had different means and standard deviations. However, we were able to compare scores from the different exams by converting the values into their associated z-scores. If you were to standardize an entire variable, then we would have a similar result. We'd be able to compare the values in the same way without losing the normal or approximately normal shape of the distribution. The two pictures at the top here demonstrate that concept. The one on the left with a mean of 100 and what looks like a standard deviation of 15 or 14, and the one on the right with a mean of 0 and a standard deviation of 1, the standard normal distribution. Notice that standardizing this variable only changed the scale of the variable, but not the shape or where the individual values are in relation to the mean. Below is an example of that concept. A soda can dispenser has a mean fill volume of 12 ounces with standard deviation of 0.12 ounces. What is the proportion of cans that have fewer than 11.9 ounces? Draw and label this area for ounces and z-scores. If we demonstrate the normal curve with ounces, we would label the mean of 12 in the center and label 3 values to the left and 3 values to the right of 12 based on the standard deviation of 0.12. This is demonstrated on the left curve where ounces is the axis. I will zoom in to make this more clear. We are trying to find what proportion of cans have fewer than 11.9 ounces. So we need to label 11.9 between 12 and 11.88. A little bit closer to 11.88 though numerically. So I'd probably draw 11.9 around here. That'd be my value for 11.9. And since we're trying to find the proportion of cans that have fewer than that, I would shade the area below 11.9. If I were to standardize this, I would do so by calculating the z-score for 11.9. The z-score can be found by taking 11.9, subtracting away the mean of 12, and dividing this standard deviation of 0.12, resulting in a z-score of negative 0.83 approximately. If I then graph this z-score on the second curve on the right, I would find negative 0.83 between the mean of 0 and the standard deviation of negative 1. A little bit closer to negative 1, so I probably graph negative 0.83 around here. And since we want the proportion of cans to have fewer than that z-score, we would shade the area to the left of that. Note that these two graphs are identical aside from the axis, aside from the scale. Now that we have the graphs created and we have the z-score calculated, we're going to go to the normal probability table in Appendix A to determine what proportion is to the left of the z-score of negative 0.83. Here in Appendix A, we have the normal probability table representing negative z-scores. There's one page that represents negative z-scores and one that represents positive z-scores. Reminder that our z-score that we calculated was z equals negative 0.83. In order to find this probability on the table, what we are going to do is look at the rightmost column that has z as a label and take the whole number and first decimal place of that z-score, negative 0.8. We're going to scroll down until we find negative 0.8. Just pretty far down, we find it here. That designates what row we are in, and then to find which column, we need to look at the last decimal place of that z-score, which was a 3. So if I look at the top, I see 3 or 0.03 here as the fourth column to the left of the z-score. So then, if I highlight all the way down for this column, and then the row of negative 0.8, we find that that cross section there will represent the proportion that I'm looking for. In this case, 0.2033. That will be the proportion to the left, or the area to the left of the z-score that I am looking for. I know it is the area to the left because the picture at the top of this page demonstrates a shaded region to the left of some indicated value. So we have 0.2033. Since we were looking for the area to the left, and we found that from the table it was 0.2033, we will label it like so, 0.2033. That being true for both the z-score area, 0.2033, as well as the one with ounces as the scale. That 0.2033 is going to be our final answer. Note that when we looked at the normal probability table, we found the area to the left. However, if you were looking for the area to the right, we want to keep in mind that the normal probability table in most books will give you the area to the left. So, if you would instead like the area to the right, you must first find the area to the left and then subtract this amount from 1. That is how you would find the area to the right. Furthermore, we will always recommend that you draw a picture first and then find the z-score second. For any normal probability situation, always draw the normal curve first. Label the mean, the standard deviation, and observed value, and shade the area of interest. The picture will provide an estimate for the probability. After drawing a picture to represent the situation, you can compute a z-score to determine how many standard deviations are between the mean and the observation of interest. Or you can use technology, for example GeoGebra, to find the proportion of values that are below or above the observation of interest. The next page will show some consequences and some things to keep in mind when using the normal probability table. Important consequence: areas under the curve corresponding to the data value x are the same as the area under the curve corresponding to the standardized score z computed from x, meaning that when we convert to a z-score, that's not going to change the probabilities below or above the z-score we would find from using that table. When using the normal probability table to find areas under the curve, first we have that z-scores are found in the margins of the table, as demonstrated earlier. The left margin has the whole number and the first decimal place. The top margin has the second decimal place. So if you have a z-score of -2.35, we find -2.3 on the left and 0.05 in the top margin. The probabilities are also symmetric around the mean mu sub 0, which means the area to the left of z equals -1.5, which means this shaded region to the left of that is the same as the area to the right of positive 1.5. This is pretty handy for us because this will allow us to find the probability to the left of -1.5, which the normal probability table is very useful for. And we can use that to say what the probability to the right of positive 0.15 is, if we instead do not want to subtract the area to the left of positive 0.15 from 1. Thirdly, probabilities are found in the body of the table and represent cumulative areas from the left. The value found in the body of the table where -1.4 on the left margin meets 0.01 on the top margin is 0.0793, so that'd be a z-score of -1.41. And therefore the area to the left of -1.41 in the graph of the standard normal distribution is 0.0793. The probabilities of being greater than a particular z-score can be found by subtracting the table value from 1. So, in the previous situation, where we found the probability to the left is 0.0793, if we instead wanted the area greater than that, this black shaded region, Then I would find that by taking the area of 0.0793 and subtracting that from 1, resulting in 0.9207. If you need to find probabilities between two particular z-scores, you can find that by subtracting the table value of the smaller z-score from the table value of the larger z-score. If I want the probability between negative 1.32 and 1.75 for z-scores, I would find the area entirely to the left of the z-score of 1.75, which is 0.9599. And then I would subtract away this red shaded region, which is the probability to the left of negative 1.32, that being 0.0934. If I subtract away that from 0.9599, what I will have left over is simply the area in between those two values, which is 0.8665. Lastly, a z-score associated with a particular probability can be determined by finding the given probability, or the closest one, in the body of the table and reading the corresponding z-score off the margins. Therefore, if we are working backwards, we have a probability and we're trying to find the z-score that relates to that, we can look at the center of that table and work outwards to try to find the z-score that relates to that. For example, if you have a probability of 0.2061 to the left, we find that where negative 0.8 on the left margin meets 0.01 on the top margin. So for the probability of 0.2061, the associated z-score is negative 0.82. If a given probability is not found in the table, find the closest value. If you have any further questions, be sure to review the example videos or ask your instructor.